In Module 5 of Chapter 11, we looked at the construction of the binomial tree that's used mostly in this book. However, there are many ways of developing binomial trees, all of which provide the same option prices, not necessarily for a fixed value of n, where n is the number of steps in the binomial tree, but as n gets big, all of these methods will converge to the same option price. So while you have some latitude in picking a binomial model, you can have the confidence that if you develop a binomial lattice that's fine enough, namely the number of steps to expiry is relatively big, then your pricing will not depend greatly on the particular model you choose. So why is it that, in fact, a model, there are many ways of developing a binomial model. And here's the intuition. The intuition is that a binomial model requires three parameters. It requires a u value, the return in the upstate, a d value, the return in the downstate, and p, the probability of an up. Those three parameters determine a binomial model. Now, in most binomial models, the binomial model is calibrated to only have two features. Namely, it's calibrated to have a targeted expected return and a targeted volatility of returns. So intuitively, a binomial model has three unknown parameters that you can choose, and most binomial models are calibrated to only introduce two constraints on those three parameters, the two constraints being the expected return and the volatility of returns. Consequently, we have three unknowns in two constraints, and one has a variety of latitudes about how to introduce, if you will, in a discretionary way, that third constraint. So we'll see in this module a couple of other ways to do it. This slide makes the point I made in my introductory remark that as the period length h goes to 0, all of these models, if properly implemented, will produce the same prices in the limit. No matter how one constructs a tree, the risk-neutral probability is always going to have this form, and the price of an option is always going to be, as we saw earlier, the expected present value. So in the tree, you might define D and U differently, but the P star that works and produces the correct value of an option will always have this same form. The U and the D will be different, and then the point I made earlier is that the U and the D will depend on the number of steps of the lattice, and as those number of steps increases, all of these models converge to the same prices. In the Cox-Ross-Rubinstein binomial tree, which was the original pricing implementation of a binomial to stock options, was a simple, somewhat simpler model, and that was that U is equal to 1 over D. In other words, you can see that here U and D are constrained. Remember I mentioned that the one typically has three constraints that can be imposed, and in this model there was an additional constraint that U and D would be reciprocals of each other, and then the mean return and the volatility provide the rest of the tree. There can be some theoretical problem if H is large, and that is, you recall we have this important constraint that the return on the risk-free rate has to be between the U and the D value. With this particular model, it's possible to be in violation of this constraint when H is big, but this is not a problem because we always are interested in making H small anyway.